Cool. So welcome to what is the last lecture of this mini course in particle detectors and relativistic quantum information protocols in quantum field theory. The so now this is lecture 5. The the goal of this lecture is to basically discuss everything that we swept under the carpet for the past lectures. So the idea here is that we will be discussing I think that there's no better way of putting it than to say considerations about particle detectors. So we're going to discuss the details that we should have discussed before, or we could have discussed before, but we didn't because we wanted to see what we could do with the detectors before actually starting to discuss this part, which is a little bit more well, there's some interesting part to it, but it's a little bit more on the details, more than what you can actually do in the overall considerations. So today we'll talk about these considerations about particle detectors. Specifically, we want to know how do these models connect to physical systems that couple to quantum fields, okay? And what are the issues that arise from these models? So there are 3 main references that I'm going to suggest here, if you're interested in this. One of them is a paper that I put out last year, which is basically about the definition of particle detectors in curved spacetimes from non-relativistic basically wave functions function quantum mechanics. The other one, and this is basically how it this paper essentially discusses how to actually define particle detectors in curved spacetimes in a way that well, there's a consistent formalism for everything that's happening there. The other one is about how these models break covariance, and we're going to briefly discuss this today, but we have a finite amount of time. So basically, if you want to see the details, broken covariance, you should take a look at this paper. And the other one, it is a very detailed discussion on faster than light signaling, or how you could, in principle, how these effective models have a limitation in the sense that they predict that it's possible to signal faster than light. However, we understand these as limitations of the model, understand the regimes where we shouldn't be using the model, basically, exactly due to these predictions. Okay, there's some other papers about each one of these things, trying to give like the more, I guess, comprehensive or the more general in some cases, but like the more updated references on this. But there are many more references to talk about it. If you're interested in this, feel free to send me an email or something. Cool. So I guess the key thing is that the models we discussed so far are all effective models. We didn't really use quantum field theory to describe any of them or anything like this, right? So they're effective models. And the reason that they're effective models is because we wanted to describe localized quantum systems. If I ask you to consider a localized quantum field, then either you're going to have to prescribe some sort of external potential, or you're going to have to solve a highly interacting quantum field theory, both which we just can't do properly nowadays. Okay, so basically the descriptions we used were in the regime of non-relativistic quantum mechanics. So they were non-relativistic. And we're going to discuss it in detail. What do I mean by this? But of course, because of this thing, we're going to find issues with causality and covariance. Okay. Okay, nice. So first, before really diving deep into these issues and things like this, let's first see how you can kind of like derive a particle detector model of the sort of the ones that we have been discussing here. Okay. So the first question you're going to ask is how to describe a non-relativistic quantum system. Hopefully, you would be able to answer this question up to some extent by yourself. But the question here is in spacetime. This is the key thing that we want to add to this description. Okay. So in order to study this, the first thing that we're going to do is to consider a quantum system with one with one position degree of freedom. So basically, it's a wave function. Okay, degree of freedom. So wave function. And this basically means in 3D, of course, because we want to do things in well in the world where we live with without having to specify the systems too carefully or whatever. When I talk about wave functions, it's 3+1. Okay. So basically, we have a position operator, a momentum operator, and we have a Hamiltonian, which will promote time evolution. Okay, and these are the things that we care about. This is the system that we're going to describe. So, in principle, the system is defined in Galilean spacetime, right? We have a t, we have an x, we have a p. So, so this is described in a Galilean spacetime. But we want, of course, to talk about relativistic spacetime. So this is not like I'm going to put a Minkowski for this first example, spacetime. So how can we kind of like tie things together? Is there any regime where someone sees Minkowski spacetime pretty much as being Galilean or something like this? And the answer is yes, right? If you're standing in Minkowski spacetime and you're very small, or you have access to a very small region, too fast, it'll be very hard for you to decide whether you were actually in Minkowski spacetime or in Galilean spacetime, unless you had access to very fast things or tried to signal to very far away or things like this. But it will be very hard in principle. So the idea here is that we will describe the system in a frame comoving with let's say the observer that sees the Hamiltonian h of x ET. So the idea is, if someone sees a harmonic oscillator, if I have a harmonic oscillator and I see this as a harmonic oscillator in this non-relativistic description, I'm not going to not consider an observer which is moving very fast relative to this and then try to put this harmonic oscillator in this weird frame. I'm going to pick a frame which is co-moving with this harmonic oscillator, and I'm going to basically pretend that this harmonic oscillator is immersed in Minkowski spacetime instead of the Galilean spacetime where it is. Now, for the harmonic oscillator, the wave functions are localized, which means that within that small region for small enough energies, it's pretty much possible to approximate the to use the two descriptions. There won't be too many discrepancies between the two descriptions. That's the basic idea. Okay. So basically, the idea is that not too many differences in this frame between relativistic or non-relativistic description. There will be differences, of course, but they will be very small. Okay. Cool. So basically the assumption here, so that this is true, is that in this frame, the expected value of the non-relativistic energy of the particle should be much smaller than mc squared. And from now on, I'll stop writing the c squared. If I say m, assume that there is a c squared there. Maybe I'll write it sometimes, but basically if I don't, just yeah. And this is, of course, the rest mass of the particle. And what I mean by H non-relativistic is that the total Hamiltonian that we're going to use here is always going to be, sorry, there's no hat there, is always going to be the mc squared plus the non-relativistic Hamiltonian, which usually is something which is like the standard p squared divided by 2m plus a potential v of x. So we have to take into account this term here, okay, this mc squared, because in relativity, this term will matter a lot due to redshift. So basically, whenever general relativity is concerned, the absolute energy is important, not only the relative energy, right? And of course, remember that this comes from so this comes from the expansion of the root of m squared plus p squared, right? It's going to be the relativistic energy. Then if you expand this, of course, I have the potential as well and things like this. But the point is that's where this m comes from. And you'd have to add the factors of c. But cool. So now, what will change then in this description? Well, not too many things. So not many things change in this case. But the key things that we are interested in describing here is that the x operator, it will become associated with the position in this specific slice. So the idea here is, say we have this potential that's trapping a particle. There's someone co-moving with the potential, the particle, and everything. Even if we have a t and an x, and then this wave function will be defined for every t in a different slice, the idea is that this foliation, the x operator basically measures position in this specific foliation, and you cannot ask using this position operator what would be the position of the particle in another spatial slice, in another spatial foliation. So you're fixing that in this non-relativistic description, okay? And very important, this description only should work, or approximately work, in this specific foliation. Which is co-moving with the localization of the particle. Now, how do we get the system to interact with a quantum field, which is what we want? Okay. So now that we have this description for the wave function in spacetime, which is tied to the foliation, in order to describe the interaction with the field, basically, well, we get the field and we will couple it in a very simple way. Let's see what comes out of it. So, interaction with quantum field. And what's going to show up? Well, let's phi of x, which is basically a phi of dx, be a scalar quantum field. And we will couple a monopole operator, which will be dependent on the position operator. So let's mu be a position operator, dependent observable in the localized non-relativistic quantum system Hilbert space. So this is localized non-relativistic quantum system. Okay, I'm just not going to write the whole thing because it's a little bit too much. All right, now the interaction Hamiltonian will be prescribed. Notice that I'm prescribing interaction Hamiltonian in this case, not a Hamiltonian density. It will be prescribed as this. Or even in the interaction picture, should even add time dependence to this position operator. So the position operator evolves in the interaction picture due to the free time evolution. And here, the key important thing is that we evaluate the quantum field at the position operator. Okay? Evaluate the field at x hat, the operator. All right. So why do we why do we want to have this? Well, basically the idea is that the quantum particle feels the quantum field as it is at each position, and then the shape of the wave function will determine how much it sees the field or how strong is the coupling, together with the expected value or the value of the operator mu in the wave function. Okay. Now, if we do this, what we can do is that we can expand this interaction Hamiltonian in the position basis, and I'll use the position basis, which is vary in time according to the interaction picture. I'll define this in a second, but the idea is not too complicated. So these cats xt prime, the idea here is that we want the xt. Let's put the vectors here because they're all three vectors. We want this at the position operator that is time dependent to satisfy the orthogonality condition, basically. So we want this to happen for each t, taking into account the time evolution. So basically this xt, it's e to the I ht times the position operator x. Okay. And of course, if we want the wave function, the then what's going to happen is that if we contract the state psi n with this xt, then we're going to get an e to the I, the energy level associated to psi, and here we get the conjugates. Okay, so for eigen functions. Cool. All right. So what happens now is that inserting this identity here with the x can just go through the mu and the phi. So basically, I'm going to replace these by their values here. So this projector here is just going to replace each one of the x of t by simply x. So this will become an integral d3x of mu x and phi of tx. And of course, we keep the projectors here. But now, I will assume that this H has these discrete energy levels, and that span the whole Hilbert space. And if they span the whole Hilbert space, now I have a basis of these, and I can add two identities, and I'm going to add an identity here and an identity here for these size. And what's going to happen is that I'm going to get a sum over n and m lambda QFT, the integral d3x of the mu doesn't have any operator dependency anymore, because it was an operator basically only due to the position operator. So I think that for clarity, it's better to not have the hats on the mu's. Just mu is a function of the position operator. So mu of x, here we will get still the phi of the x. But now we have the two identities that we're going to add, a psi n, xt, xt, and a psi m, psi m. And this can be rewritten basically as a, so using this expression up here, and yeah, this can be rewritten as lambda QFT. Now we get a, actually, okay, so if we want to recover the particle detector, let's do integral d3x of whatever is inside here will be like an effective Hamiltonian density, right? Because there's the integral of the d3x that gives the Hamiltonian. The sum over n and m of lambda QFT. Now we're going to have this mu of x, and we'll get from this psi n with the xt, we're going to get a psi n star of x, and also the complex phase. From the other one here, we're going to get the psi m of x. We get an e to the minus I, then we're going to get e m minus e n t. And the other two terms will be the psi n, psi m. So this term here is an interaction Hamiltonian density. And this is kind of similar to the UDW model. Let me just define some things here. So if I define this as an f n m of x, now you see that for each n m, the Hamiltonian density, it looks basically like one of the terms that we had in our particle detector model. It's going to become even more explicit very soon. But the idea is that we have this e to the I en minus ent, and here we're going to have, I forgot the field, sorry about that. So I have the quantum field, phi of t x, and we have the psi n psi m. Okay. And then just to really recover the model, if we focus, so focusing on two energy levels, E and G, which I'm going to call the ground and excited and ground, right? With the energy of the ground state being smaller than the energy of the excited state, then we can just define an omega, which is the energy of the ground minus an energy of the ground state, which is the energy gap. Then the effective interaction Hamiltonian density for this case will be lambda chi t fgg of x times gg. There will be another term, fee of x times e. But then there will be the two terms which we actually care about, which are e to the minus I omega t coming from this term here, fge g plus fe of x e to the I omega t e g. And basically, this term here is a sigma minus, and this term here is a sigma plus, because this one maps the excited state to the ground, and the other one maps the ground state to the excited, right? So the idea here is that we recover the particle detector model. So basically, this is a particle detector model with an extra term which commutes with its free Hamiltonian. And I can't, sorry. Oh, there we go. Which commutes with its free Hamiltonian. Okay, so the idea here is, look, we started with any wave function quantum system, okay? Then we consider interaction, which was of specific form here. So there's any observable, which is a function of the position operator. We coupled it to the field by using the fact that the position operator represents the position within that slice of that system. And then simply by expanding this term, or this Hamiltonian, in terms of the eigenbasis of the Hamiltonian, what we found was that we recovered pretty much the underlying detector model when we restrict ourselves to two energy levels. Okay, that's the basic idea. Now the key point here is the system can be anything, right? You could think of this as like a hydrogen atom that is interacting with one mode of the electromagnetic field, or something, or one polarization of the electromagnetic field, for instance, which is super well described by classical field, or things like this, right? So, and in fact, there are many physical systems which do correspond to particle detectors in many limits. For instance, the interaction of atoms with the electromagnetic field, whenever exchanges of angular momentum are not relevant, okay, between the atom and the electromagnetic field. So these models that are these qubits that we're coupling to the field and using to dump information to the field and whatever, these are actually physical systems. And as a matter of fact, anything that couples to a quantum field up to there will be a regime for anything that couples to a quantum field such that this thing will behave like an unreduced detector, apart from very model specific details. Okay, so this is quite a general model that reduces to a smeared UDW detector. If you want to recover the point, like just use the approximation that your wave functions are very, very localized, and then you get something that looks like a very localized system. Okay, and important comment here is that one can consider more general fields and quantum systems and then one will be able to precisely reproduce atoms interacting with electromagnetism. Then with no approximations whatsoever, you're still going to get this localized non-relativistic quantum system coupled to the electromagnetic field. Nucleons interacting with neutrinos. So neutrino detection can also be modeled by systems like this. Any system with linearized quantum gravity and or for instance superconducting qubits interacting with electromagnetism, which is probably where we're going to see the first examples of experiments being done in related to entanglement harvesting, or we're going to see entanglement harvesting space like entanglement harvesting being done for the first time with using superconducting qubits coupled to the electromagnetic field in an optic fiber, which is effectively a one-dimensional electromagnetic field. I'm just going to put some references here. If you're interested, check it out. You can take some notes. The 12779 with quantum gravity, you can see this one for atoms coupled to quantum gravity, or if you want to see entanglement harvesting from gravity, you can check the paper below. And finally, this one, a little bit about how to model this, not about the experiment itself yet. You can check this paper about modeling. And there are a couple of other papers that I'm not going to hear about the experimental things, but basically look for Adrian Lupasco if you want to see the experiments. So experiments, or soon to be held. Well, experiments involved with this concept, check Adrian Lupasco. Okay, cool. Nice. So basically, we can model the interaction of non-relativistic quantum systems with quantum fields in flat spacetimes using particle detectors. And basically, if you generalize the concept of particle detectors to curved spacetimes, to allow for, well, if you just use a slightly more general definition of particle detectors, I would say that the a particle detector is any localized system that couples with a quantum field theory, right? So in this case, anything that couples with quantum field theory, yeah, in one way or another, will be a particle detector, sure, and we'll have many similarities with these models that we were studying here. So cool. So next step, curved spacetimes. Now, the issue here is that we want to do non-relativistic quantum mechanics in curved spacetimes. And of course, if I say non-relativistic and I say curved spacetime, something should kind of bother you, right? Because it's non-relativistic even for closest, but for special relativity. How are we going to incorporate general relativity into this? Well, these that we can employ an approximate formulas, but in order to do this, we need to talk about Fermi normal coordinates. And I'll be very brief to talk about them, but basically these will be the keys so that we can talk about position and momentum operators. All right, so Fermi normal coordinates, crash course. Let's z of tau be any time-like curve in a given spacetime, of course. U mu is for velocity. And A mu is for acceleration. So basically, we have that U mu is d z mu d tau. Tau is the proper time. We have that A mu is d u mu d tau, where this d tau is basically u nu nabla nu of u mu. Okay? Now, so proper acceleration and for velocity, nice. How do we build the Fermi normal coordinates? So pick tau 0. Okay, so there's the trajectory here. We're going to fix the tau 0. Now, at tau 0, we fix E0, we define E0 of tau 0 as being the for velocity at tau 0. So there's a E0 of tau 0. Now we want to complete this basis, so we pick EI of tau 0 such that basically if you compute the inner product of the E0 with the EI, this is 0, and the inner product of the EIs with themselves is delta J. So you complete this to an orthonormal basis. So there will be the space-like vectors. So in this case, there will be an E1 of tau 0 and an E2 of tau 0. Now the third step is to extend this frame to the whole curve. And we do this by Fermi transporting. So we Fermi transport the frame E mu of tau 0. The Fermi transport is you basically solve this differential equation here. 2 plus 2 u mu a nu v nu equals 0. So this is like a parallel transport, but it's like a parallel transport where you take into account the rotation of the curve, okay? But it's a special kind of parallel transport which takes into account the motion of the curve. So basically, if you have a helix and you parallel transport a vector around the helix, the vector doesn't rotate. But if you Fermi transport a vector along the helix, and your vector is initially pointing at the center of the helix, this vector will always keep pointing to the center of the helix. So it's like a transport which is kind of naturally adapted to the motion of the curve. And this preserves the angles. So basically, this implies that from this, we get an E mu of tau. So we get a full frame that is defined everywhere in the curve around here. And this frame will be such that it will still be orthonormal for all tau. Next up, we'll shoot geodesics. So what do I want to say for each tau? So we shoot geodesics from z of tau with initial, sorry, this is not how it's spelled, initial, with initial tangent vector given by v, which is xi ei of tau. So basically, you shoot geodesics in all the directions orthogonal to your forward velocity. So in the okay, wait 1 second. Let me restart the share so that we don't get. Hopefully, it's going to work better now. All right, but the idea is we shoot geodesics in the directions of these emus each tau. Yeah. So what we end up with in the end is something that basically looks like we're getting these effective rest spaces for a trajectory. So in a given point here, if I shoot the geodesics in all the directions, I'll get an effective rest space for this observer, for an observer that undergoes this trajectory. Okay, so we do this in every possible direction. And this, what's going to happen now is that I can actually assign coordinates to each one of these surfaces. So this defines surfaces sigma tau, and we can use the initial vector just for completeness here. So there's a sigma tau where the geodesics don't meet. So I'm just going to say that if the geodesics meet, then we don't care about these points. These points are not a part of any surface sigma tau. Okay. So then we can use the initial vector xi ei to define coordinates in sigma tau such that a point with coordinates x1, xn is at a proper distance of root of xi of z of tau. So basically, I say that this point here, x has coordinates x1, x2. If this initial vector here has coordinates x1, e1 plus x2, e2, and then I shoot the geodesic in that direction, and I ran it so that I ran it until I cover a distance of the square root of xi. Now you do this for each tau. This defines a coordinate system around z of tau. Basically, not two, around z of tau. So the region where these coordinates will be defined will basically be something that will look like this. Maybe it's larger, maybe it's smaller, depends on the details of the trajectory and when the geodesics meet and everything like this. But now you have these local rest surfaces and everything like this. An important fact from this is that notice that this is the coordinates, of course. The coordinate system is basically you use the tau. Sorry, let me write this properly. Use the tau to parameterize the surface, and the xi to tell you which point you're talking about. So the coordinate system is tau x1 xn. You can do this in any number of dimensions. We're going to restrict ourselves to 3 plus 1. And these are the Fermi normal coordinates. And then finally, notice that the field partial tau is only normalized. So partial tau equals u tau at the trajectory, but not necessarily away from it. So basically, g of partial tau is going to be -1 if and only if all of the space coordinates are not if and only if, but the in general for all spacetimes, yes. But basically, the condition that ensures normalization is that you are in the trajectory itself, which means that all of the xi's are 0. All of the coordinates which tell you how far away from the trajectory you are 0. Okay. Cool. This is the crash course in Fermi normal coordinates. There are many references about this. There's one very good that I usually recommend people. You just get it here because it's on the other sheets. This coordinate, this reference is Poisson Vega. It's a paper from 2011. It's on the archive. Amazing reference. Whenever I mention or need to remember anything about Fermi normal coordinates or many things about general relativity actually and geometry and Lorentzian manifolds, I go to this paper. Very, very good. Okay. So recommend it. You can also find some a little bit more detailed review in the lecture notes for the first lecture. I didn't have time to cover this back then, but well, now this is what we're gonna need about these Fermi normal coordinates. Okay. Nice. So now we come back to our previous issue, which is we want non-relativistic quantum mechanics in curved spacetimes. So basically, we need to define the x and p operators in curved spacetimes. So we need to define the x and p operators in curved spacetimes. Curved spacetimes. Remember that when we did this in special relativity, basically in Minkowski spacetime, we picked a frame that was comoving with the center of the potential or the center of the particle, the wave packet, And then we found a way, basically, of defining these things there, right? So in this case, we're going to do something very similar, uh, but using the Fermi normal coordinates instead of using inertial coordinates in Minkowski spacetime. So the idea here is that the Fermi normal coordinates are the closest that to the inertial coordinates in Minkowski spacetime that you can get for a specific trajectory. So they're the closest description to what an observer undergoing a given trajectory sees. Even the space coordinates that correspond to proper distance and things like this, right? And the partial tau along the curve is the for velocity and things like this. So yeah, basically that's how they're used to describe things close to a certain trajectory. And if things are not moving too fast around that, then it's possible to use these coordinates to do pretty much what we did in the other case. So let's use the Fermi normal coordinates. Around the trajectory of the center of potential that traps the wave function. This trajectory, let's just call it z of tau. The Fermi normal coordinates, let's just call them tau x. So our Fermi normal coordinates. And of course, we also have the radiation sigma tau that comes with it. So we have these items now. Now we can define the where our wave functions live. Oh, sorry about that. I need to 1 second. Oh, sorry about that. Cool. There we go. All right. So we can define where the wave functions live, and we're going to say that they live in these rest surfaces. So they belong to the space of square integrable functions, L2 sigma tau. And the inner product in these surfaces is naturally given by the integral over sigma tau using the induced metric, using the induced surface element in sigma. So the integral over sigma tau d sigma of psi star of x phi of x. The point here is that this d sigma is root g sigma d3x, and this g sigma is the induced metric in the surfaces sigma tau. Okay. Now what we will do will be to build an extended Fermi frame. So extended Fermi frame. And the idea here is if there is a trajectory, and we used to have the Fermi frame here with the E0, E1, and E2, but we also have the surfaces, the rest surface around this. Now what we're going to do is that we're going to parallel transport this frame along each one of the geodesics that we had from before. So now we're just going to extend this frame locally around the trajectory, okay? So basically we build this frame mu, which is parallel transport the frame E mu along the surface sigma tau, and using the geodesics, from before, so from the construction, so the ones which are emanating from this the point z of tau, from the point z of tau. Okay, nice. Cool. Now, what we need to do is to define the position and momentum operators in this thing. If we want our wave functions to live in this surface, right, in these rest surfaces, then well, we need to define position and momentum operators. So we have the kinematics, and then we can talk about the dynamics. Okay. So the position operator is defined as follows. Each one of its components basically acts on wave functions. Oh, sorry about this hex. The hex should most definitely not be there. Oh. Okay. Okay, so each component of it is just going to multiply the wave function by the Fermi normal coordinates xi. Okay, and the position operator itself as an operator would just be written in this extended Fermi frame, basically. Okay. So basically, you're just multiplying you're multiplying the wave function by components. Okay, and if you want to get a vector out of this, you describe this vector in the Fermi frame, basically. Okay, this clearly self-adjoint with respect to the previous inner product, and very important, and the momentum operator acting on sign. This will be a little bit more weird. It will be minus I g sigma to the 1/4 partial xi g sigma to the 1/4. Again, g sigma is the square root of the determinant of the induced metric. Okay. Cool, but then you're going to have these two terms, and the justification for the first one is that these match proper distance from z of tau. Okay. The justification for P is basically the set of things which are satisfied down here. So the set of things that are satisfied, which one can show that basically if psi equals 0 at the boundary of the sigma tau, so if psi is really confined to the region where these rest surfaces are defined, then for any such psi, the conjugate of each one of these xi's is xi itself. So basically, you can show that position and momentum are self-adjoint, but you can also show that the canonical commutation relations are satisfied. And as an exercise, check these. So verify these. It's basically using integration by parts in the inner product of the L2 sigma tau. Okay. Nice. So this is basically the kinematics, right? So this is the description of our wave function. So we have a description which is reasonably consistent for localized wave functions. in curved spacetimes. And this satisfies everything that we could want it to satisfy. Now the question that we have to address is the dynamics. So the dynamics. I'm not going to give too much detail into the dynamics, but the idea is that if we started, if we had the Hamiltonian h of x b t for the particle in, say, in flat spacetimes or in the moving frame in moving with the potential, right? In Minkowski, moving and in inertia, right? In Minkowski, then the idea is that we will the Hamiltonian will change, right? And one note just closed. Sorry about that. We open it again. Ooh, I lost a lot. That's annoying. All right, I'm not going to rewrite everything, but basically for the dynamics, what we're going to do is if we had this in inertia or in the truly non-relativistic description from before, what we're going to do is to look at the Hamiltonian h of x p tau, where reinterpreted. So the idea here is this becomes the x operator from x from above, from the Fermi normal coordinates, and this is the p from above, and this is the proper time. Now you can wonder, well, will this just work? What do you mean by this? Right? It's like I have a harmonic oscillator in an inertial harmonic oscillator trapping my wave function here. If I start running with the harmonic oscillator very, very fast and accelerating and everything, will the description just be exactly the same? And you would have a point. This doesn't work. If you just do this, you will be missing something very, very important, okay? Even if the potential is constant in the Fermi frame or something like this, still there's something that you will be missing, which is that there is redshift. So it's this plus redshift. What do I mean by redshift? What I mean is we're describing the particle around we're describing the evolution of the particle from Cauchy from slice to slice, right? And these lines, they may be curved, right? The vector partial tau which connects these two, which is the time translation, is not normalized. Okay, so the redshift factor that you will find due to this to the surfaces possibly being wiggly due to curvature, and also due to the acceleration of the trajectory, which will make them bend back and forth. So the redshift factor when you're using the proper time of the trajectory to describe everything will be gamma, which depends on tau and x in principle, it means that function spacetime, 1 divided by the norm of the tau, which is going to be given by this quantity here in terms of the metric, and this is the inverse of induced metric. But basically, it's and this is the determinant of the, sorry, this is the absolute value, square root of the absolute value of this quantity here. This is 1 over the norm of the one form theta, which is basically the form associated with the infinitesimal interval of time, okay, that elapses between one surface and the other. So basically, in order to incorporate the redshift, one would consider one would consider the Hamiltonian gamma of tau x h x b tau. But now the issue is, well, classically, you could just make the product of these terms and everything would work. However, in quantum mechanics, there's things that don't work like this, right? Because there's an X operator, there's a P operator, and then the product of these will not be self-adjoint. So basically, not necessarily self-adjoint. So another issue, and we need to somehow fix it. We're going to see that we don't actually have to fix it. So there are many ways of fixing this, right? So someone could say, well, instead we're going to use 1/2 this plus the Hermitian conjugates. And now, well, now it's self-adjoint by definition, right? I mean, if you restrict the domain. But the point is, this will not matter. So the self-adjointness, the issues with self-adjointness do not matter in this non-relativistic regime. So if H non-relativistic is much smaller than MC squared. What do I mean by this? Well, you see, this gamma factor that we have, this gamma of tau x, this gamma of tau x that we have, we can actually compute this in terms of the, or at least to leading order in curvature and acceleration, we can compute this, and this term is given by 1 plus AI xi plus 1/2 r0i0j contracted with xi xj plus terms of order size of, or position operator cubed, or size of your wave function cubed, curvature squared, and acceleration squared. So basically, the leading order corrections are given by this. And now, if you compute the product of gamma with your Hamiltonian, you will find that this will be, well, even better, right? This Hamiltonian here, it will be the M term plus the non-relativistic Hamiltonian. So basically the idea is we will pick up M times gamma plus gamma times the non-relativistic Hamiltonian. But the non-relativistic Hamiltonian is already much smaller than the mass and anything else that you're going to get this Hamiltonian. So basically, the issue here is that this product here can be written as m plus your non-relativistic Hamiltonian plus the other corrections, the m ai xi plus the m over 2 r 0i 0j xi xj, and plus terms which are small simply because they are the product of non-relativistic energy of your system with things which are of the order of the acceleration of the trajectory in natural units times the size of your system. All of these terms are very small if you put them together, right? We're already assuming that the non-relativistic energy is small. On top of this, we have that the acceleration and curvature are sufficiently small so that we can use these Fermi normal coordinates and employ them. So in the end, what we find is that one node closed again. 1 second. I'll just open it again. But what we find in the end is these corrections in terms of acceleration and curvature, which will which are reasonably which are reasonable, and this is independent of the order of your ordering of this product. So basically, just again, this will be m plus h and r plus m ai xi plus m over 2 r 0i 0j xi xj plus small terms. So this means that your Hamiltonian will be exactly what you had before, plus these corrections, which are due to the acceleration of your trajectory and the curvature of spacetime. So this is the change in the dynamics that will happen to your wave function because you're describing this in terms of well, in a curved spacetime undergoing a given trajectory, and there will be this. So basically, this term here is like a tidal force term. So it's basically squishing or contracting your wave function due to the different gravitational field, and this term here is basically a wave function inertia. Basically, it lags behind. It's like a lagging. It lags behind the direction of acceleration. So if it's accelerate in one way, the wave function kind of stays behind a little bit. Okay. Cool. So we have this correction of the Hamiltonian, and this works to leading order in these non-relativistic corrections, right? Nice. So this is how you describe your wave function in curved spacetimes. Then of course you can couple it to a quantum field. You're going to find a lot about this in the first reference that I gave today. But the idea is that it basically you can do the same expansion that we did for flat spacetimes in curved spacetimes, and everything works out pretty much exactly in the same way. You recover the covariant terms that we got and the covariant integrals and everything, and everything will basically work again. So again, if you want to will work in the same way. But you're going to get the model in curved spacetimes this time. You can also generalize it to other fields. You can also do pretty much whatever you want. Cool. Nice. So there are two other things that I want to mention today, which are very brief, luckily. One of them, I think it's the most interesting one, so I'll put a little bit more time in this. It's on the breakdowns of covariance. So breakdown of covariance. There are consequences to using non-relativistic systems to try to in curved spacetimes, right? Of course. And these consequences are basically you're going to violate covariance and causality up to some extent in some cases. So the microcausality condition. Maybe you remember it from maybe you discussed this in the QFT in curved spacetime course. If you didn't, then I'll just state it here to you. It states that any two observables which are spatially separated must commute. So for x, this is my space. And then it's associated with the idea of like that you can perform independent measurements in space-like separated regions, which is related to the idea of causality, basically, but subtly. But for us specifically here, this condition is essential so that time ordering is uniquely defined, or is covariant, or is independent of the choice of time parameter. So what do I mean here? If you have the time ordering of the product of O of x and O of x prime, this time ordering is theta of t minus t prime times the product of OX prime, or should I say plus, theta of t prime minus t, O of x prime, O of x, right? So the first one comes first, and the second one comes after. Now, you can rewrite this as being so you can rewrite the second term using the commutator, basically. So you're going to get something like this plus theta of t prime minus t. Now here we're going to get O of x prime again. But for this, we have to add the commutator. So the commutator just cancels this term and adds back the previous one. And now you're going to see that this term and this term, they're the same, apart from the theta. But theta of t minus t prime and theta of t prime minus t is just one. So this will be O of x prime plus theta of t prime minus t. And here we're going to get the commutator, O of x prime, O of x. Now, so basically here, use that theta of u plus theta of minus u is 1. Okay, nice. So now if I choose another time parameter, this has to be the same as, well, or if I choose another time parameter and I try to time order using this parameter, now what we're going to have is going to be this. So basically enforcing this, right? Now, if we enforce this, what happens is that these two are going to be equal. So these are equal only if, well, then if we enforce this, of course, the O of x prime is going to cancel. So what we're going to have is only if theta of t prime minus t minus theta of tau prime minus tau on this commutator is equal to 0. And this has to happen for every t and tau time coordinate. Now the key thing here is if I fix two events on spacetime, x and x prime, then these two notions of time order can only disagree. Again, these two notions of time order can only disagree in so I'm just gonna stop the screen share and start again. For some reason today is worse than usually. Give me 1 second. Let me just yeah. Just rewrite the thing here before I start the screen share again. All right, we'll go back to Zoom. There we go. Sorry about that. Okay, cool. So this is the equation that we had, and this has to be true for every t and tau time coordinate. Now the point is, if you have two time coordinates, say that we have events x and x prime, okay? If they're time like separated, of course, like you have to have like t prime t the two time coordinates have to agree. Okay, that's the idea. If they're time like separated, and this is simply because there's no like if I want to foliate this, so I want to foliate this with space like surfaces or something like this, there's no way for me to come up with two foliations such that uh, x touches a sheet before x prime does, right? So time like separated events are always fine in the sense that the for any two time coordinates, these heaviside thetas will always agree. Okay. However, if I have space-like separated events, oh yeah, and this is also true for space-like, also space-like. Sorry, light-like. Now, if I have space-like separated events, now I can pick a foliation such that x prime happens first, such as this one, or I can pick a foliation such that x happens first, such as this one. So x happens first, and x prime happens first. So in this case, basically, what happens is that for space-like separated events, so this implies that they're always time coordinates such that tau minus L prime will be different from t minus t prime. Okay. And in that case, oops. And in that case, we must have so time ordering will be independent of time coordinates only if so only if the microcausality condition is satisfied. So basically, if the operators commute when they're space-like separated. Okay. Nice. So, and the time ordering is very important for us because you remember that when we prescribed the unitary time evolution operator, we actually needed the time order. So time ordering is important. Remember that the u is the time ordered exponential of minus I, the integral dv of hi of x. And now the point is, this doesn't depend on a time parameter only if hi commutes with itself for space-like separated x and x prime. Okay. Oops. All right. Now, in this mirrored UDW model that we talked about briefly, so in this mirrored UDW model, okay, then we had this Hamiltonian for a detector, which was lambda, monopole operator, space times mirroring function, quantum field. Okay. So every quantum field theory satisfies microcausality. Okay. This is a postulate of the theory. Basically comes from the fact that the field commutator is the causal propagator, which only has support in the causal future and causal past, but not when the field is when the points are space like separate. Okay, nice. So here, if we want to compute the hi and the commutator of hi with itself in different spacetime events, we'll find that, well, so for space-like separated points, the field will commute with itself. Lambda is just a scalar function, commutes with itself. Lambda is just a number, commutes with itself. So basically, you can take everything away from this commutator, including the field operators, assuming space-like separation. Yeah, and here, assuming that x is space-like separated from x prime. But now we have this commutator here, which is the mu of tau with mu of tau prime. And this is an issue because remember that the mu of tau, it was the e to the I omega tau sigma plus e to the minus I omega tau sigma minus. So now if we do the products, mu of tau prime, what we get will be only two terms, because sigma plus is 0, and sigma minus with sigma minus is 0. So we're going to get e to the I omega tau minus tau prime sigma plus minus. And another term, which is going to be e to the minus I omega tau minus tau prime sigma minus sigma plus. And now, of course, if you want to compute the commutator, basically what you have is this expression times this expression when with the tau and tau prime switched, right? So basically the commutator of mu with itself, this is going to be this term minus itself. So we're going to get e minus itself with the tau switched to tau prime. So for the sigma plus sigma minus, we're going to get this sigma plus sigma minus, and we're going to get the same thing, but with a minus. Yeah. So for the other one, we're going to get e to the minus I omega tau minus tau prime minus the same thing with the switched tau and tau prime, sigma minus sigma plus. And then, of course, the first term is the same as the second one, and they're both 2i times the sine of omega tau minus tau prime, sigma plus sigma minus sigma plus, and this is just sigma z. Okay, so basically the commutator of the sigma matrices is not necessarily 0 for tau different than tau prime. So basically and of course, if you go back to the commutator of the Hamiltonian, you'll find that this commutator is only 0 for space-like separated events. So for x prime. So this is it. If and only if. Let me remove this implication error here because it's confusing. Yep. Yep. Okay. So this happens if and only if tau minus tau prime is 2 pi n divided by omega, basically. So almost done. Okay, so this means that the time evolution that we prescribe with the particle detector, it depends on a notion of time ordering. Okay, so U depends on time parameter. Oh, then the time parameter, basically the idea here is that tau is the privileged time parameter. Because we are describing that we're using this Fermi normal coordinate time in a specific trajectory to describe the wave function as if it was non-relativistic plus some corrections. We are privileging this tau time parameter. So basically what we should write is that U is the time order exponential with respect to the parameter tau of the integral dv of the hi of x. This is well defined, but of course it's not covariant, right? It's not covariant because it depends on the specific choice of time parameter tau. But the good thing is that the consequences of this are not super bad. So basically, in this paper here, 2006.12514, it was shown that if you use a time parameter t and then you use a time parameter tau to compute it, so two different time parameters, you're going to see that the difference to order lambda squared is going to depend on whether or not your initial state for your detector commutes with your, this is the free Hamiltonian basically, so this is the free Hamiltonian. So basically, if you start at the ground state or at the excited state to leading order and perturbation theory, this breakdown of covariance doesn't happen. And if you don't commute with your free Hamiltonian, if you're not in the ground or excited state or in a mixture of these, and you want to use this formula, then what happens here is that this E, it's given by minus 2y, an integral over a specific region, dv prime, lambda of x prime. This will be the Weidmann function of the quantum field times the sine of omega tau minus tau prime. And I have set theta here. Cool. And this region here, it is the set of all points in m times m prime, such that x is space-like to x prime, and the notion of time ordering disagree. Sorry, I put the prime in the wrong spot. There you go. All right. Cool. So basically, notice that this will okay. The fact that the integrals happen the support of the detector spacetime smearing and within a region where the points have to be space-like separated, means that basically if the size of the detector, the spatial proper size of the detector is too small, then there will be no violation of causality, of covariance whatsoever. So basically, the summary here is, I mean, there is no leading order violation of causality if your initial state of the detector is a mixture of the ground and excited. So you're safe in this case. The gapless detector is safe. And it's safe because this omega here is zero, so the sine of zero will be zero. This E correction term will be zero, and also like the commutator of the interaction with Hamiltonian with itself will always be zero. And the difference between two notions or two time orderings it depends on the region where the detectors viewed in such a way that it implies that point like detectors are fine. And again, we're right against time, getting close to the time where we end. Indeed, it's ready to be a while. Yeah, gapless detector is safe. And basically, the last conclusion is that point like detectors are safe. So they're independent of this notion of time order. Maybe the very last thing that I'm gonna say is just not really gonna say much about it. I'm just gonna tell a story. It's a pretty complicated story to tell, even in quantum field theory without detectors. So there's just a particular case. And it's very, very short. It's basically a Sorkin's problem. And the idea is very simple. You have this happens even in classical field theory. So if you apply a local operation in this region here, okay, then of course you can only affect anything in your causal future, right? But I'll say that someone else applies a local operation here. And of course, this person will only be able to affect its causal future. But now if someone else couples to the field or whatever, right, performs an operation here, in principle, you're going to be, well, okay, so A cannot signal to C because they're space like separate, right? C is outside of the causal future of A, so A cannot signal to C. But if you apply a local operation in B, what will happen is that whatever is happening here might transmit basically information from A to C. So there might be there's no local operation might allow A to signal to C. Okay, that's and then the probabilities in C might depend on A due to this non-local operation that is applied in B. And of course, the detectors can apply these local operations as well. And the point is that even in quantum field theory, it's very hard to classify which operations you can actually perform in order to see whether there will be causality violations or not. This is being studied a lot. I will leave a couple of references here. If you're interested, just gonna write them down here. And this is the last thing that I wanted to say today, apart from the I guess that final remarks and apologies and thanks. So these are for specific case of detectors. Then we have Sorkin's original paper, from 93, 02, 019. So this is sorting. Then we have for modern formulation of this, we have this paper here. Modern formulation in quantum field theory. There's a problem in QFT, not necessarily with detectors. So this is a more modern formulation. And then finally, there's this last paper here, which shows that even just with QFT, this happens. Cool. So that's basically it. These are the most important things that I want to say. So basically, don't use your detectors in these scenarios where they violate causality, or if you do, make sure to check that the violations are negligible compared to anything else that you might be interested in measuring. Okay, this is very important. It is a limitation of the model, but it's very hard to describe states in states that are localized, okay, in quantum field theory or in any other case. So there's no relativistic description so that it works. Let me just do one thing here. You're gonna stop seeing me for a second. Just want to say, yeah, there you go. Should be back now. Yeah, there you go. All right. So if you joined the course up to this point, then congratulations. There was a lot of technical calculations being done here, and it requires a lot of patience, I guess. But I really wanted to show basically how to do these calculations, because I guess that most of these things you're not going to find explicitly in papers. This was a slightly short course. I think that there was so much more that could have been said, but at the same time, it's impossible to do this in a mini course. So yeah, apologies, I could not go over absolutely everything that I wanted, but hopefully you learned something that is that you wanted to learn here, and that can be useful in the future. Feel free to reach out. Let me leave my email here in the chat. Feel free to reach out if you have any questions or want to discuss or anything like that. Let me just say perimeter institute. That's yay. There you go. You can email me. Feel free. And the last thing is that I will post the lecture notes and the video recordings probably tomorrow at some point. Today I have to pack because I have to fly tomorrow morning. So I'll most likely not be able to upload everything, but you should be able to find it in hopefully tomorrow, if not the day after. Okay. So thank you very much. And let me stop the recording.